All right. So it's 1:31, and I'm just gonna get started then. So this is misleading. Today we're not. I forgot to change this part. That's not true. But today we're going to be talking about. Well, we learned a lot about the evolution of stars in general, and so now we're going to be talking about groups of stars and why, kind of like, what does all this stuff have to do with the rest of astronomy in general. Um, so what I wanted to go over at first was all the layers of astronomy that we have. So it's from the very beginning, we have, like, at a very low level, we have what we call planetary science, which is stuff to do with planets. Then we talk about solar astronomy, which is when we're studying the sun. And then we have stellar astronomy, galactic, extragalactic stuff, and cosmology, talking about bigger and bigger and bigger scales. So I'm just going to dive into each one of these for a little while. So the one that we are the most familiar with and we have been studying this whole time is, well, it's stellar astronomy. Right? This is the study of stars and how they evolve. Right? This is what we've been looking at. And mostly we've been talking about star evolution and how they're formed. Right? So we know that stars start out in molecular clouds and then they become protostars, right? From protostars, they journey to become main sequence. And after that, they become what we call red giants as they begin to run out of hydrogen to fuse. And that's when a star begins to approach, it's a star death. And after it undergoes a supernova or undergoes a planetary nebula, and sheds its layers, it either becomes a white dwarf, or if the star is really, really, really big, then it becomes a neutron star. Or if it's very, very massive, it can even become a black hole. All right. So this is all the stuff we've been studying so far. That's what's involved in stellar astronomy, focusing on all different types of stars. Going one level down, we have specifically solar astronomy, which has everything to do with studying our very own sun. All right. So our own sun is what we call a G2 main sequence star, right? G2 meaning that it's on the HR diagram, right? So we know our HR diagram, and we have our main sequence running through here. No, there's better, more like this. Right, so G2 is somewhere right there in the middle. It's a kind of a yellowish type of star, and it's about that luminous. So that's what G2 tells us. And we know the sun's about 4.6 billion years old, and since it's in its main sequence, it's going to be fusing hydrogen into helium, and it's going to keep doing that for a couple more million years. Some other phenomena that goes on in solar astronomy are sunspots, prominence and solar flares, stuff that we talked about in one of our first lessons. Let me see if we can get back here. All right, so we have our different pieces of the sun that we like to study. All right, we have the core, radiative zone, convective zone, and all these different other pieces of the sun that we study in solar astronomy. And how we do that is we send these probes out to the sun, or we point our telescopes just straight up at the sun and just take in a lot of data from it. We know about the core and how it's in what we call a self-correcting hydrostatic equilibrium, right? And that's why it is so stable. We have our different zones and how they kind of convect and form these convection cells that kind of look like these honeycombs, and how this is a top layer of what those convection zones kind of look like. where you see there's convection going on all over the place, and you're forming all these cells. And this is what we call the photosphere, which is one of the outermost layers of the sun, which shows the end of the convection zone. And on top of the photosphere, we have the chromosphere, which is what's on top of that photosphere and has all these spicules and all these filaments that kind of look like fiery grass, right, that we talked about. And then on top of the photosphere, we have the corona, which is where all the really interesting stuff happens, where we have our solar prominences, like this, which is caused by the magnetic field of the sun, where we have our solar flares, right? So some really interesting stuff going on in the sun. And that's what's studied in solar astronomy. And one of the things that I don't know if not everyone stuck around for, but why do we care about, hold on. Yeah, why do we care about studying our very own sun? And the reason for that is that there are a lot of dangers that come with the sun, right? So what are some of those dangers? So the sun, what does the sun give us, right? It gives us heat. It gives us light, which are necessary ingredients for life, right? So that's why the sun is so important to us. For us humans in particular, the UV light that comes from the sun helps us metabolize or create vitamin D in our own bodies. If we didn't have vitamin D, then you would start to turn a lot paler, you would begin to feel really sick, and you would lose all your energy. And by going out in sunlight, that actually helps make you healthy. Also in the recent decades, we've also started to have more renewable energy, right? We have our solar panels, right? Solar panels that we can face towards the sun and generate electricity, right? So these are the ones that we have down on Earth, right? These are our solar panels, right? You see these on people's roofs. But another thing that people have theorized about and is what we call a Dyson sphere, which is, imagine if you had your sun right here, right? It's shining all this light. And then imagine if you put a bunch of solar panels right around the sun, like that, right? If you blocked out, or not really blocked out, but put solar panels right next to the sun, then that energy would be a lot more strong than you would get down on Earth. And that's what's called a Dyson sphere. If you cover the sun in a bunch of solar panels, and you get a lot of energy. But that's all in theory. We haven't been able to do that yet. But these are different ways that the sun helps us generate energy. But with all that energy, there also comes danger, right? Because think about it. You have a sun, a ball of plasma and gas sitting there floating in space at 10 million degrees Kelvin. That's really, really powerful, right? And what gets created are what we call solar storms, which is when the sun has a really weird interaction in its own magnetic field, and it releases a bunch of this hot plasma, this hot gas out into space. So here's what kind of happens when a solar storm hits the Earth. Or, yeah. Wait for it. There. So what this is called a coronal mass ejection, or as you see in the top corner, a CME. So CME is when, well, as I said, when the sun has a really weird interaction in its own magnetic field, and it causes a lot of the sun's outer atmosphere to be ejected into space. So if you see right here, what's in the red and the yellow, that actually is a very small coronal mass ejection. And if you see from all these green lines everywhere, right, there's a green line here and green lines here, right? These are all what we call solar wind. They're like very tiny miniature coronal ejections. because the sun is always releasing its atmosphere off. It's always giving off, gas and stuff as solar wind, releasing itself. But a coronal mass ejection is a really, really big, like wave of solar wind. And normally these small solar winds are completely fine, because if you guys have ever heard of the northern lights, right? Or what we, in scientific terms, what they call the aurora borealis, that's actually caused because of, hold on, let me turn off notifications. All right. That's actually caused because of this solar wind hitting the Earth's atmosphere and generating those really pretty lights. But if you see that really massive storm right here, right, this super red area, that's really dangerous. And if you see Earth is right here, right, Earth is over here. We just barely missed that massive storm. If that storm hit the Earth, that would be a really, really big issue. And here is why. I have the next video here.
Higher density plasma.
So what video is showing, or what all these lines are, is showing the Earth's magnetic field, right? So we have, a North Pole up here, a South Pole down here, and you can see the magnetic field, looping around and looping around, right? And so if you can see all these layers here, what the magnetic field is doing is protecting the Earth from the sun's magnetic solar wind. Because, as we know, inside the core, that's that super hot plasma, all that fusion going on, it creates really hot ionized gas. And what the key point is, the word ionize here. It's really, they're these charged particles, right? And charged particles, well, they're either positive, they're either negative, but if those were to hit, it's basically electricity in space, right? And our Earth's magnetic field helps channel and protect the Earth from all that like space electricity, from interfering on our into our own electronics, right? Think about your computer, what you're sitting here watching me on, right? Think about your lights, think about hospitals, think about like, things that keep people alive, right? All of the technology and planes and everything, all technology that relies on electricity, is based off of, electrons, right? It's based off of these charged particles. So if you have a bunch of these charged particles that come in from space and hit Earth, then that kind of messes everything up. It would create a lot of short circuiting. All the technology would completely fail, right? So that's why Earth's magnetic field is so important. It protects us from that solar wind that comes off from the sun every single day. But whenever a coronal mass ejection hits, that's when it becomes very scary. And this video kind of goes into depth about that.
And stronger magnetic field carried within the CME strikes Earth's field and significantly alters the structure. Here we see the dramatic.
You saw the difference in, the change in Earth's magnetic field, right? These lines in the very front here got a lot like looser. You see that area in the front became a lot smaller, because that's because a really strong coronal mass ejection hit the Earth's atmosphere, hit the magnetic field, and kind of blew it away a little bit. But as you can still see, there's still a lot of lines here. The Earth is still mostly protected, so it wasn't that bad. We were able to get off pretty easily.
Changes in Earth's magnetic field and the shape of the magnetopause as the CME passes Earth. But close to Earth, the magnetic field is largely unchanged. Earth is protected from the intense solar event. This is the case for a rather ordinary CME. In this example, a CME launched by an X3 flare from December 2006. But what would happen in the case of a more intense event, such as the Carrington event of 1859? With the aid of similar computer models as before, we can explore some of these possibilities. Here, a much stronger CME compresses the magnetic field between the Sun and Earth and generates more density in the bow shock, represented by darker red. The front of the magnetopause is pushed much closer to the Earth than usual. Even the field and plasma trailing behind the Earth are more strongly distorted. Shape
All
of the
right. So that guy said a lot of really fancy words. The first one that he said was magnetopause, right? So that's the most important one. So you see that layer, like this layer right here. This is what he's talking about, the magnetopause. And what that refers to is the barrier, the magnetic barrier that protects the Earth. And what he said was that as the CME hits the Earth, you can see how much closer that magnetopause is pushed up against the Earth, right? This is the magnetopause, basically. And look how close that is pushed up to it. And another, which shows that Earth's magnetic field is getting destroyed here because of how powerful that coronal mass ejection was. The second thing he pointed out was all this kind of trail behind the Earth. And what this is plasma that hit the Earth and then was rebounded off of it, basically. The Earth like absorbed a lot of it, but it couldn't absorb all of it, and therefore that was released out from the back here. What that shows basically is that this coronal mass ejection was so powerful that it would have decimated everything electronic on the Earth, and there was still more plasma to spare. So it could have like destroyed the Earth's electronics multiple times over. That's what all this plasma behind behind the Earth is showing. But I don't know if you guys saw the timestamp, but this was in 1859, right? So back in 1859, we didn't have that much technology, right? You know, we had very, very, very basic technology. People were still riding around in horses and stuff like that, right? So when the coronal mass ejection hit the Earth, it didn't really change anything because we didn't rely on technology as much. But if this type of coronal mass ejection were to hit Earth today, then that would cause wide scale damage, right? As I was saying, you know, we have so much technology that we rely on every single day, right? Your lights, your computers, your cars, you know, your grocery stores, everything would completely just break down and society would just stop functioning if this type of coronal mass ejection hit the Earth. And so that's why it's so important to study solar astronomy, to understand our own sun and the dangers that it poses to us so that we can avoid something like this from happening and better protect ourselves. So yeah, that's kind of solar astronomy, right? Going one level down even further, we have planetary science. So planetary science is, well, it's in the name. It's the study of, well, the planets, moons, comets, asteroids, and everything within our own solar system. Of course, the same knowledge can be applied to, you know, exoplanets, planets outside of our solar system, but we know the most about planets within our own solar system. So that's what I'm going to be focusing on. So what this image is showing, it shows all of the planets to scale, basically. So so Mercury is actually this small, you know, Venus is actually this small, and stuff like that. So these are all to scale, which I think is nice. Because most images that like watch, if we were going to Google and just search up, let's see, solar system or solar system to scale. Okay, let's click this image. Okay, that's not an image. Sure, let's add to photos. All right. So this is showing all the planets what we mean to scale. meaning that if Mercury was actually this small, then Earth would be this much bigger than it, right? If Earth is this big, then Jupiter in real life is actually that much bigger than it in real life. So basically what this is showing all the planets as they would look in real life, which I think is really important because oftentimes if you search up on Google just solar system, you're not going to see the planets to scale, right? Like look at this. Look at this image. Look how much bigger Mercury is and the Earth is compared to Jupiter, right? Or look how small the sun is compared to the rest of the planets, right? These are not to scale. The same thing here, right? If you look at the diagram here, Mercury, well, look, the sun is looks super big, but it's really, really small compared to how it should look. Jupiter is roughly the same size as the Earth, right? There's not too much of a difference there. Same thing here, right? Nothing is really to scale. This is not to scale. This is not to scale. So another thing that I want to make sure that you guys get out of this course is that in astronomy, people and like artists and illustrators really like to make space look better than it really is. They try to paint pictures and make illustrations that make the Earth or solar system or space look prettier than it really is. And like I think it's cool to have some really nice illustrations, but sometimes they trick you into believing certain things are true that aren't. For example, how big each of these planets are compared to each other. The sun is much bigger than that. Jupiter is supposed to be much bigger than that. All these planets are out of scale, right? So you can see how many images there are of planets and suns that are out of scale compared to ones that are actually accurate. And so this is accurate. The sizes are accurate, but the distances to each other are not, right? Obviously, the sun is not that close to Mercury. Mercury is not that close to Venus, is not that close to Jupiter, right? They're all not that close together. In fact, all the planets are actually really, really far away. And when I was on Wikipedia searching up this lesson, I saw a really cool looking, a really nice graphic here. This. So it says here, distances are to scale, objects are not. So the objects are not how big as they are supposed to be, but the distances between them are. So let's start here on the very, very left. So we start at the surface of our sun, right? And it's about this far to Mercury, all right? From Mercury, then we have our inner four planets, what we call our rocky planets, right? They're rocky because they're not surrounded by a bunch of gas. Mercury, which is a really big ball of rock. And we have Venus, then we have Earth and Mars, and then there's a really long distance. We have our asteroid belt. After our asteroid belt, a really, really long distance. Then we have Jupiter, and then even more distance. I'm still scrolling. Look at that, still scrolling. Then we finally see Saturn. Now we're in our gas giants, still scrolling, still scrolling, still scrolling. Finally, we find Uranus, and we're still scrolling, still scrolling. Finally, we see Neptune. Let's scroll some more, and finally, Pluto. So the distance between planets in the solar system is way, way bigger than you might think. Because before I started looking into astronomy myself, I always thought, I'd seen all the images on Google. I always thought, oh, the planets are all kind of close to each other, right? But no, in reality, Look how far away they are, right? They're so far away. This kind of puts it into more perspective here, which is showing the distance between the orbits of all the different like planets, right? So you see all the here on the very left, with this is millions of kilometers from the sun. So the sun is obviously is at 0. Mercury is right here, barely any distance away. Then we have Venus, Earth, Mars. They're all right here next to the sun. Then we have our asteroid belt right here. Then there's Jupiter, which is roughly 750 million kilometers from the sun. Then Saturn, which is 1,500 million kilometers from the sun. And then you have Uranus and Neptune and Pluto. So it's really, really far away. The inner planets to Neptune and the outer planets. A really, really big distance. What I thought I could do here is I could also go through a few like quick facts about each of the planets, kind of. So we can start here at Mercury. So okay, so each of these symbols mean a certain thing. So the circle with an arrow next to it means how far away it is from the sun. So Mercury is roughly 57 million miles from the sun, so pretty close. And then the circle with a line through it is representing the diameter of the planet. So here we have Mercury, which is only roughly 5,000 kilometers in diameter. So rather small. Some interesting facts about it is that because of how close it is to the sun, it doesn't have any what we call geological features. Just right here. No geological features. What that means is that if you imagine Earth, right? Earth has, mountains and ridges and all these tectonic plates that form all these really cool, rifts and shifts inside the crust. But Mercury has none of that, because basically how it was formed is just that it was just a ball of rock, and because of how close it is to the sun, any time it tried to form any geological feature, the solar wind would just blast it away. Solar wind blast surface. That's why it doesn't have anything interesting on it at all. It's basically just mostly a flat ball of rock. Because solar wind is just blasting anything that could possibly exist away on it. Then we have Venus, which is a little bit further out, and some cool things. And it's about 100 million miles away from the sun and about 12,000 kilometers in diameter, which is pretty similar to the Earth. So Venus and Earth, they're about the same size, but Venus is the hottest planet in the solar system at an average surface temperature of 400 degrees Celsius. That's how, yeah, it's really hot. Surface temp. And the reason for that is because Venus has a very, very, very thick atmosphere. So you can imagine at Earth, we have our atmosphere, right? And Venus's has a lot more, greenhouse gases. So the Earth has maybe an atmosphere about this thick or something like that. Then Venus's would be like this thick, right? It's way, way thicker, has way, way more carbon dioxide and methane inside of its atmosphere, which traps all of the sunlight that hits it. And that's what makes it so hot. Another thing that is what's really interesting is that scientists believe that Venus is really volcanic. So volcanic. One reason for that is that because the surface temperature is so hot, they imagine that within the core of Venus and in its mantle, it would also be very, very active and really molten. And as a result, the surface of Venus would just be basically like a whole, basically like a lava planet, kind of, where you have constant volcanic eruptions all over the place, and you have a lot of new earth and new ground being created all the time because all the volcanic activity. So even though Venus is really similar to Earth in its size and its distance to the sun, it's probably not going to be habitable just because of how hot it is on the surface and because of all of that volcanic activity. All right. Next, we come to Earth. Well, obviously, there's a lot to say about what's so unique about the Earth. First is that it's one of the only planets with liquid water on its surface. It's the only planet that we have what we call intelligent life on it. And it has roughly, its atmosphere is mostly nitrogen and oxygen, which is something that we don't find on any of the other planets. So Earth is oxygen rich. It's also roughly 150 million miles from Earth and 12,000 kilometers in diameter. All right. Next, we have Mars, right? So Mars is a bit smaller than Earth, roughly about almost half the size in terms of its diameter. But Mars has 2 moons, has Phobos and Deimos. And it also has a very thin atmosphere, has a roughly 16% of Earth's atmosphere. And is mostly made of CO2. So that's all carbon dioxide. So what scientists think what happened to Mars was that Mars used to be a very active planet like the Earth. One of the reasons why we want to study Mars, so we've been sending so many rovers to it and trying to find out previous life, is because what scientists believe Mars used to be was a very active planet with an active core, right? I don't know if you guys know about Earth, but the Earth has a molten core right in the center, a core of iron. And that iron is always shifting around and moving. And its movement is what actually generates our magnetic field. But what scientists think happened to Mars is that Mars at one point also had a molten iron core. But over time, for one reason or another, that iron core began to cool down. And as it cooled down, it became less fluid and stopped generating a magnetic field. And as it stopped generating a magnetic field, well, then it has no protection from solar wind like the Earth does. And since it has no protection from solar wind, its atmosphere got blasted away by the solar wind. That's why the atmosphere on Mars is so thin. That's why they think the atmosphere is so thin, because everything else is being blasted away by the solar wind. On Mars itself, there are a lot of mountains. One of the tallest mountains in the entire solar system is on Mars, by the name of Olympus Mons. Tallest mountain in solar system is on here, whose name is Olympus Mons. Let me just double check the height of Olympus Mons. Olympus Mons height. It is actually 21.9 kilometers tall. All right. So let's compare the two between Mount Everest and Olympus Mons. Compare Mount Everest Olympus Mons. I misspelled. That should be okay. There. So that's how tall Everest is. Then if you took 2 Everests, almost 3 Everests, that's how tall Olympus Mons is. Here's another image. There's Everest right here. There's Olympus Mons. So obviously very, very, very tall. Maybe another look at it. Oh, here's a look at it from space. Here's Everest, and here's Olympus Mons. How Olympus Mons got to be so tall was that it was actually because Olympus Mons is it's a dead volcano. And as the volcano died off, that's what created that type of its shape. The reason why we want to study the Martian surface and why we think there used to be life on it is because there are these crevices running through Mars. Actually, let's just find this. Evidence of water on Mars. Sorry, did someone say something?
I said people believe there was water, right?
Yeah. Not only do we believe there's water, we have very good evidence of it. Right? For example, let's take a look at these. Right? Do you see these tracks running through the ground? These types of tracks are only carved by water. Do you see these lakes, these giant these craters, and how there are these tracks running through and carving all through the crater? That's evidence of previous water. So here, evidence of water, Mars with oceans. What people think is that Mars at one point did look like this, right? With water all over the planet. And there's kind of like this one giant continent and then one giant ocean, right? So that's what people think Mars used to look like. But obviously, as it lost its atmosphere, that water began to evaporate away. And that's why Mars, as we see it today, is really, really dry. But there's evidence of these lakes all over Mars. And scientists, as they continue to discover, they find even more evidence. Recently, in the past few years, the Opportunity rover found these things called blueberries, what they call blueberries. So Opportunity rover blueberries. These. So what these blueberries are they're caused by basically water that's been trapped inside a mineral. And that mineral is embedded inside a rock. So and the reason why they're so blue is because that certain mineral was attached to water, basically. And it was frozen inside these marbles. So this is evidence that there was some type of water in this area at Mars at some point. Right? And there's a lot of, as I said, there's a lot of evidence of there being ridges and valleys and these crevices and lakes all being carved by water all across the Martian surface. So that's why scientists want to study Mars so much, because if there's water, there might be life. All right, so that's a lot about Mars. Moving on. Next, we have the asteroid belt, which is, it's self-explanatory. This asteroid belt is filled with a bunch of asteroids, a bunch of rock, a bunch of stuff that's floating around right outside Mars and before Jupiter. Some interesting things to point out about it is that there's Ceres here. Ceres is the first, what we call dwarf planet that we discovered. So we call it a dwarf planet because it's about the same size as the moon, but it's not exactly orbiting the sun really, because it's kind of it's inside the asteroid belt. So that's what we call it, a dwarf planet. But that's Ceres. Sometimes asteroids, inside the asteroid belt, asteroids will collide with each other, right? As they collide with each other, sometimes they get sent out of the asteroid belt. And as they get sent out of the asteroid belt, they might fly towards the inner planets or fly towards the outer planets. And that's why sometimes we have collisions or have, if you hear sometimes in the news, like, oh, an asteroid just passed by Earth within so-and-so 1,000 kilometers, right? Because that's what happens in the asteroid belt. Stuff collides and stuff gets sent out. All right, now we've reached what we call the outer solar system, which is after the asteroid belt. And these are our gas giants. So the biggest one is, of course, Jupiter. So Jupiter actually makes up 99% of all the mass that orbits the sun. So that out of everything here that orbits the sun, 99% of it is found in Jupiter. So Jupiter is a really, really big planet, right? But because it's a gas giant, it's mostly just made out of gas. There's not really any rock in it whatsoever. Some people talk about, oh, what would happen if you land on Jupiter? But there isn't really a land. There's nothing to land on. It's just gas. It's like mostly methane, a bunch of carbon dioxide, some sulfur inside of it. It's about 20 times the Earth's mass. But because it's just gas, that's why it's so big. So interesting things to point out about it is that all these bands are storms that go on on Jupiter. And of course, the most famous of these storms is its red eye, right? Here, let's just take a look at some Jupiter. You can see the swirling of the storms and everything. If you can imagine, like imagine just like constant hurricanes going on Jupiter. That's basically what's going on. You can see how scientists have already labeled all the different regions because, of course, this is all about planetary science, right? They study the different planets and they've already named all these different belts, zones, storms on Jupiter. So yeah. That is Jupiter. One little known fact about Jupiter is that it actually has rings. So you can't see the rings with a naked eye, but it does have rings, very, very, very faint rings. So something like that. But they're very, very, very faint. Nothing as cool as Saturn's. But that takes us up. Oh, another thing is that it has 29 satellites. So a satellite is another way that we just basically call a moon, something that orbits a planet. That's what we call a satellite. And Jupiter has 29 of them. So that's pretty crazy. Moving on. Next, we have Saturn, which is another gas giant, right? The most interesting thing about Saturn, of course, is its rings, right? And it's really, really pretty rings. These rings are actually made out of, just gas and mostly just like really small, fine dust and ice. And one interesting thing about these rings is the rings are actually getting further and further away from Saturn every year. I forgot exactly how much they're getting away from Saturn, but basically as they get away from Saturn, these outermost rings out here are beginning to dissipate. They're kind of being flung out into space, never to be, and no longer become a ring. So, back when the dinosaurs were around, Saturn used to have a lot more rings and really thick rings. But over time, those rings have begun to dissipate over and over and over. That's Saturn. Next, we have Uranus. The funny thing about Uranus, I guess, is that you can see it in the diagram here, how it rotates like this, right? It actually rotates vertically, which is really interesting. As to why that Uranus is like that, we're not too sure. Scientists have their theories. They think that Uranus might have collided with something early on in its formation, and that's what caused it to tilt so far, but we aren't exactly sure. Yeah, that's Uranus. Next, we have Neptune. Neptune's very similar to Uranus, except it's a lot denser, and it's not orbiting like sideways. It only has one moon, while most of the other giants have a lot of moons, right? Look at all these moons. But Neptune only has one. It's Triton. I don't think there's anything else too interesting to say about Neptune. Neptune also has rings. I forgot to mention Uranus and Neptune both have rings, but it's the same thing with Jupiter. They're so small and faint that you can't see them with the naked eye, but they do exist. And beyond Neptune is what we reach what we call the Kuiper Belt. So the Kuiper Belt is similar to the asteroid belt, where it's just a bunch of rock floating in space. But the Kuiper Belt is a lot wider and a lot thicker and a lot denser than the asteroid belt. The Kuiper Belt is also where Pluto resides. So Pluto, as you know, has no longer been classified as a planet. One of the reasons is because it's part of the Kuiper Belt. Inside the Kuiper Belt, there are some very, very interesting other dwarf planets that this highlights. So you have Eris, which is actually pretty normal. You have Maki, which is also honestly pretty normal. I think the most interesting one here is Haumea. So I'm going to pull up a picture of Haumea. I spelled it wrong. But this is Haumea. So the first thing that you notice about it is that, one, why does it look like an egg, right? And the reason for that is that because it's spinning so quickly. When something spins, as you know, it gets kind of fatter at its edges, right? It kind of flatten out like that when it spins super fast. So Haumea is actually spinning actually about this quickly. And as a result of that, that's what causes it to flatten out so much and kind of look like an egg. It's just spinning so fast that it looks like that. This is, of course, this is an artist's rendition of what Haumea looks like. This is the actual image that we captured of it. But you can't really tell from this image because it's really bright. But using radio or other types of frequencies of light, you can actually tell that it's a really flat, elongated shape. And some artists decided to come along and make an animation of it, which is pretty cool. But yeah, you have some really interesting dwarf planets in the Kuiper Belt. But yeah, that's the structure that's planetary science. So oftentimes planetary science is really interesting because that's what we have the most knowledge about, right? That's the stuff that's closest to the Earth, and we can study it more directly. That's planetary science. Moving on from planetary science, now going above stellar astronomy, what's beyond stars, right? Groups of stars. So that's what galactic astronomy is all about. And specifically the Milky Way. So what I'm going to attempt to do here is basically kind of draw the Milky Way. All right. So the Milky Way, I'm going to draw two images of it. The first image is going to be the side view, and the second image is going to be a top view. But from both views, we all start at the black hole. We aren't sure if this black hole exists, but we believe, well, to the best of our knowledge, with all the data that we have from everything, from all the different galaxies we've collected from looking at telescopes, we think that at the center of every single galaxy is a super massive black hole, like massive, giant, right? This isn't the type of black hole you get from a star collapsing. That's only about 40 solar masses. We're talking about hundreds and thousands of solar masses. These are super massive black holes, and that's why they're able to create whole galaxies around them. But at the center of every our own Milky Way is a black hole, right? Around the black hole, you have what we call the central region. The central region is kind of looks like a bulge, like this. So from here, this is the central region around the Milky Way. And the central region around the Milky Way is really, really dense. It has a lot of stars in it because if you can imagine a black hole, it's sucking everything towards it. So it's kind of compacting all these stars together. So it's a really, really dense central region. From there on, you have what we call the disk. So the disk is where most of the rest of the galaxy lies, right? So here, the disk of the Milky Way kind of looks like this, like that. That's still what we'll call the central region, and then we have the arms of the Milky Way, and extending out like that. That's what the disk kind of looks like. And some more arms coming out like that. Some more arms. Yeah. That's the disk of the Milky Way from the top view. And from the side view, of course, you have your, it looks like this. And it kind of bulges and bulges and bulges. And so mostly you can't really see the black hole at this point. The same way here, you can't really see because it's the bulge, the central region around the black hole is around the Milky Way, around the black hole is super dense. So you can't really see anything there. It's all covered by stars and everything. But there we have the bulge. And then around the bulge, that's basically our Milky Way. Then we have what we have called globular clusters. So I'm just going to mark these. These are globular. I spelled that wrong. Globular clusters. And what globular clusters are just clusters of stars that all formed at around the same time. So here, let me find an image of a globular cluster. Globular cluster. Like that. So that's what a globular cluster looks like. A bunch of stars that kind of form together. Yeah, there's nothing really special about them at all, but it's just that they always form around galaxies, basically. They always form around galaxies. So there's some globular clusters here and there, here and here, sometimes in the Milky Way, but mostly outside the Milky Way, kind of like that. And then beyond the Milky Way, you have what we call the halo. So this halo region is basically the Milky Way shining its light. The Milky Way obviously has a lot of stars in it. It has a lot of energy inside it. So it releases kind of some energy out. And that's what formed this halo. Right. So this is a really bad drawing of a galaxy, but I try to take you through in the process of like the layers of the galaxy, right? So we have the central black hole moving to its central core region, surrounded by that bulge that creates, and then we have our halos, our globular clusters, and the spiraling arms of the Milky Way. So that's how I would draw a galaxy if I were to actually show you one. Structure of the Milky Way. Right? The guy who did this obviously did a lot better than me. Let's save this image. Where's photos? There. All right. So first of all, here is that top view, right? Showing that our sun, we're right here, and here are the arms, the arms of the Milky Way, the disk of the Milky Way, and then you see that central region right there. From a side view, there's the disk, there's that halo I was talking about of all that energy that it's releasing, and then you see that bulge, right? That bulge of that central region around that black hole and all the globular clusters scattered around it. Right, so that's kind of the structure of the Milky Way. Yeah, so that's galactic astronomy that people like to study. And moving on from there, after you talk about galaxies, then you talk about groups of galaxies. You talk about groups of galaxies, and you go even bigger from there. And so that's what we all put under this, what we call cosmology. Cosmology meaning the study of the universe. And the study of the universe is obviously a very broad topic. So what we have been talking about before is what we call these large scale structures, the structure of galaxies, how the structures of groups of galaxies and how everything kind of fits together. But there's stuff that's even more fundamental than that. Stuff like the Big Bang Theory, talking about, the very origins of where did all of astronomy even come from? Where did we come from, right? That's what the Big Bang Theory tries to address, saying that, all matter was all crunched up at one point and it exploded out, and that's what created the universe. That's what Big Bang Theory essentially says. We have the early universe, which is what happened after the Big Bang Theory. Literally, like, in the smallest fraction of a second after the universe, how did things form? How did protons become a thing? How did atoms become a thing? How did fusion occur? Stuff like that. That's what scientists trying to figure out what happened then. You have people studying only what we call the cosmic microwave background, which is the remnants of the Big Bang Theory that we can still see to the present day. We have those large scale structures we're talking about, the structures of giant, of galaxies, groups of galaxies, and what we call superclusters, and stuff that's even more mysterious, stuff like dark matter and dark energy, right? I don't know if you guys knew, but all the matter that you see in like the world, right? Your computer, the stars, everything, that's what we call baryonic matter. And that matter only makes up about 4% of all the stuff in the universe. So the universe has a lot of stuff in it, and 4% of it is baryonic. The rest of it is made of dark matter and dark energy. Dark matter, meaning taking up 23%. The only thing we know about dark matter is that it has mass. It has mass and it distorts and has gravity. It will affect space-time. So it will attract things together, just like baryonic matter will, but we can't detect it in any other way. And then what's even more mysterious is dark energy, which is the rest of it. So if I do this math really quickly, that should be 73% roughly. So the rest of all that stuff in the universe is made of dark energy. Dark energy doesn't have mass, we can't detect it anyway. We know it needs to exist because, if you add up all the energy in the universe, you're missing 73% of it. So that has to be something. There's something there, but we don't know what it is. That's what we call it, dark energy. So these are some really big mysteries in cosmology. And you have people from all over just trying to study this. You have particle physicists trying to figure this out. You have chemists trying to figure this out. Biologists and astrobiologists trying to figure this out. Cosmology has to do with almost every single field of science that exists, because if we can figure out things about the very early universe, if you can figure stuff out about the Big Bang Theory, dark matter and dark energy, that completely revolutionizes how we think about our world. So something on this really massive scale, something as big as cosmology, the study of our own universe, has these implications and these applications down to stuff about galactic astronomy. How did galaxies form? How did the planets form, sun form, and even stars? So we can figure out where things come from. So that was what my lesson was for today, which was we completely finished basically stellar astronomy. We learned a lot about, I introduced you guys a lot to about how stars were made, how they were formed, and through today's lesson, I wanted us to kind of branch out to all these different levels of astronomy. And because I can't cover everything in a course, right? There's so much stuff that goes on inside all of these different layers of astronomy, and I decided to only cover stellar astronomy. So that's why I wanted to have this lesson today to show that there's so much else in astronomy, and that's totally up for you guys to explore yourselves. But because I had finished like my original goal, which was trying to teach you guys stellar astronomy, and I introduced you guys to all these different layers, we still have 2 more classes left. I wanted to dedicate one of the lessons to how we study astronomy. How do telescopes work? How do satellites work? How do we take in data? How do we analyze data as an astronomer, right? And we can actually conduct some of our own science. There's some really cool, what we call community science projects, which is where you can literally look at NASA's data and then try to figure out, is that a neutron star? Is that a pulsar? Is that a black hole? Right? You can actually do that science. So that's what I want to dedicate one of our lessons to. But our other lesson is up to you guys. Is there anything from these layers of astronomy that you guys found interesting and wanted to study a bit more on? Anyone? Or type something in chat. If not, my other plan was just to talk about cosmology, kind of go into Big Bang Theory, early universe, stuff like that. Does that sound okay?
Yeah.
Yeah. All right. Cool. Because that's what I personally found to be, as much as it is interesting to study planets and stuff like that, I always found it more interesting to study like how did the universe come to be? What is dark matter? What's dark energy? I always like that stuff a bit more. So that's what we'll talk about next class. But that will wrap up today's lesson. All right. So thanks everyone for coming, and I will see you next week. Bye.